In this lesson, we're going to be focusing on resistors, and we'll be learning how to determine the total or equivalent resistance in a given circuit. Now, we'll be solving these two questions and many others. So how do we know that a resistor is arranged in series or in parallel? Suppose we are given these two resistors. Let's say that here is A, then B. This is resistor 1, and then another resistor, and then this is R2. Now, how do we arrange these resistors for them to be in series? If we want to arrange these resistors for them to be in series, we must connect the end of this R1 to this end of this R2. Alright, so if you do that, we are going to have something like this, where this is resistor 1 and then this is resistor 2. So this is point A and then this is point D. Alright, so the two resistors must be connected end to end for them to be in series. And then when two resistors are in series, the same current flows through them. So the current flowing through this resistor 1 is the same thing as the current flowing through the second resistor, but then they have different voltages. So here is V1, here is going to be V2. The same current passes through resistor 1 and resistor 2, but then they have different voltages. Voltage across this first resistor is V1, and then the voltage across this second resistor is V2. Now this is how to know when two resistors or three of them are connected in series. Now, how do we know that resistors are connected in parallel? Now, using this resistor 1 and resistor 2, let's arrange them to be in parallel. Now, when they're in parallel, we're going to connect this end, and then connect this end, and then join them to these two ends, these two nodes. Alright, that is both ends of the resistor connected to the same two nodes as the other resistor. So if you do that, we're going to have something like this. This is the first resistor, and then this is the second resistor. So we have R1 here and then R2 here. As you can see, this end and this end of this resistor is connected to this point. That is this R1 and then R2. And then this end and then this end are connected to this point, which is this and this. Alright, so here we have A and then D. Now, anytime you see a diagram like this, it means that those resistors are connected in parallel. Now, notice that when current passes through this line from point A, once it reaches at this junction or node, it will split. Part of this current will flow across this first resistor, let me name it I1, and then part of this current will flow through this R2, let me name it I2. Alright, but then the voltage that passes through this whole resistor are the same. Alright, so if here is V1, then here is also V1. In fact, let me just name it as V. So the same voltage passes through them, but then different currents. So just opposite of what we have in the series connection. So here is series arrangement, and then here is parallel arrangement. Now, the next thing we should know here is how to calculate the equivalent resistance when they are connected in series. Now, for series connection, the equivalent resistance is given by R1 plus R2. Just the summation of all the individual resistors, that will give you the equivalent resistance. And then for the resistors connected in parallel, the equivalent resistance is given by 1 over the equivalent resistance is equals to 1 over R1 plus 1 over R2. That is summation of the inverse of the individual resistors. That will give you the total equivalent resistance of the whole circuit. Now, by the time you evaluate this or simplify this, you take the inverse of it for you to get this equivalent resistance, because this is also in inverse form. You get, so assuming 1 over R1 plus 1 over R2 is equals to 1 over 7, then equivalent resistance becomes, if you take the inverse of this 1/7, it becomes equals to 7 ohms. So this is how you calculate the equivalent resistance when the resistors are connected in series and also when they are connected in parallel. Now, in case you want to solve a circuit where it has both series and parallel arrangement, you solve the series using this formula and then solve the parallel using this formula. Let's go ahead and solve these two questions. Now, solving this question, you see that this resistor and this resistor are connected in series. So let's reduce it. We have that the equivalent resistance is going to be equals to 4 ohms plus 4 ohms. Then the equivalent resistance is equals to 8 ohms. Now let's redraw this diagram and then replace these two with 8 ohms. So this is 8 ohms. Then we have 4 ohms here and then 4 ohms here. Now let's focus on this resistor here. Now if you look at this resistor very well, you see that the both ends are connected to the same wire. You get, so this is just a single wire. You get, and this single wire here, it means that any current that flows through this single wire will not encounter any resistance, whereas the one that will flow through this resistor will encounter a resistance. Now in this case, since this wire here, this one here, single wire here, has zero resistance, it is going to cancel this resistor here. It's not going to affect the equivalent resistance. So we're going to eliminate this resistance here and then work with only 4 and 8 ohms. Now if you redraw this diagram, you see that these 4 ohms and these 8 ohms are in parallel connection to each other. So the equivalent resistance is going to be 1 over RAB, that is from this point to this point, is going to be equals to 1 over 8 plus 1 over 4. Now if you find the LCM of 8 and 4, the LCM is 8. 8 divided by 8 is 1. 1 times 1 is 1. Then plus 8 divided by 4 is 2. 2 times 1 is 2. 1 plus 2 is equals to 3 over 8. Now I have that 1 over equivalent resistance is equals to 3 over 8. If you take the inverse of both sides, we are going to get that the equivalent resistance is equals to 8 over 3, which is equals to 2.667. And then this is the answer to this question. Now let's solve the second question and then many other questions. Now let's focus on this. Okay, this is 2 ohms here. Let's focus on this part. Now as you can see, this 4 ohm resistor and 3 ohm resistor are connected in series. So if I redraw this diagram, I'm going to have something like this. So this is 2 ohms, and then because they are connected in series, let me just can be drawn this way so that you see it clearly. Now this diagram here is same thing as this diagram, so you have seen clearly that it is connected in series. Here we have 3 ohms, then here we have 4 ohms. This one is 1 ohm. Now to find the equivalent resistance of these 2 ohms, just simply add them up, which is 3 plus 4 is equals to 7. So if I redraw this, I'm going to have something like this. Here is going to be 7 ohms. Then here is going to be 2 ohms. Here is going to be 1 ohms. Now, first to find the equivalent resistance here, we're going to use parallel equation, because these 7 ohms and 1 ohm are connected in parallel. So we have that 1 over equivalent resistance for parallel connection is equals to 1 over 7 plus 1 over 1. So equivalent 1 over equivalent resistance is equals to 1 over 7 plus 1 over 1. Let's assume that this is 7 over 7. So that it's going to give us 7 plus 1 is 8 over 7. Alright, that just is simply. Now, let's take the inverse of both sides. Then we see that the equivalent resistance for these two, for this and this is going to be equals to 7 over 8. Alright, so let me just redraw the whole diagram. Now we have reduced this to be 7 over 8. Now let's redraw the diagram. So we have, this is 2 ohms, and then the equivalence of this 7 and 1 that's arranged in parallel is equals to 7 over 8. So this is 7 over 8 ohms. Now notice that these two are now in series, and so the overall equivalent resistance, or the total resistance, is going to be equals to 2 plus 7 over 8. Then if you plug this in your calculator, 2 plus 7 divided by 8 is going to be equals to 2.875 ohms. And this is the equivalent resistance of the resistors that are in this whole circuit. And let's look at another example. Now suppose you have these resistors. This is 1 ohm, and then we have another one here which is 5 ohm, and then we have another one here which is this is 2 ohms, and then we have another one here which is 3 ohms. So I want you to pause this video and calculate the total resistance in this whole circuit. And the first thing we're going to do here is to focus on this parallel connection here, and then reduce it. So we have that 1 over equivalent resistance in parallel is going to be equals to 1 over 5 plus 1 over 2. And the LCM of this is equals to 10. 5 divided by 10 is 2, then plus 10 divided by 2 is 5. 5 times 1 is 5. Now 2 plus 5 is equals to 7 divided by 10. So that the equivalent resistance for these two resistors that are connected in parallel is going to be equals to 7 over 10. Then let's take the inverse of both sides. So the equivalent resistance is now going to be equals to 10 divided by 7, which is equals to, or let's just leave it as 10 over 7. Let's not approximate now. So let's redraw this our diagram. We have 1 ohm here, and then these two give us 10 over 7. So we have 10 divided by 7 ohms, and then we have another one here which is 3 ohms. So let's now find the total capacitance here, resistance. I don't know why I keep on saying capacitance. Now the total resistance here, or overall equivalent resistance, let me just write it as RT, as total resistance, is equals to 1 plus 10 over 7 plus 3. Now if you point this in your calculator, we're going to get 5.429 ohms. So this is the total resistance of the resistors in this given circuit. And let's solve another one. Now suppose we are given this circuit. So let's assume that here is 1 ohm. So let's take all of them to be equals to 1 ohm for easy computation. Now we are going to focus on this part first. Let's reduce this parallel connection. So I want you to pause this video and try this question. Alright, so we have that 1 over equivalent resistance for this one. Let me just be writing 1 over R, let me not confuse you. So 1 over R here is equals to 1 over 1 plus 1 over 1 plus 1 over 1. So 1 over R here is equals to, now 1 over 1 is equals to 1. Now 1 plus 1 is equals to 2. 2 plus 1 is equals to 3. Let's take the inverse of both sides. So I have that R is equals to 1 over 3 ohms. So the equivalent resistance of these ones that are connected in parallel is equals to 1 over 3 ohms. Now let's redraw it. We have 1 over 3 ohms here. Then we have this 1 ohm here. This is 1 ohms. And then we have this one. Let me just write it here. Then this is 1 ohm. And then we have the last one here, which is 1 ohm. Now notice that this resistor here is connected across a single wire, and this single wire has 0 resistance. Alright, so it has 0 voltage. There's no potential difference between this line and this line. In that case, this resistor is said to be short circuited. Alright, so it's going to cancel out. It's not going to have effect on the equivalent resistance of these resistors. Alright, so we're going to focus on this, and then this. So we see that these 3 resistors here are connected in series. So the total resistance now is going to be equals to 1 over 3 plus 1 plus 1 is equals to 1 over 3 plus 2. But we know that 2, so let me write this 1 over 3 plus, we know that 2 is the same thing as 6 over 3. Alright, so the LCM here is 3. We simply add the numerators since the denominators are both 3. So 6 plus 1 is equals to 7. So the total resistance here is equals to 7 over 3 ohms. Now, did you get the answer? What did you get? Let me know in the comment section. Thank you for watching. Subscribe to this channel for more videos. Also like this video, drop your comments and share with your friends. Have a nice day.